Hello YouTube, RJ. Hey, today got something on the bench. First part for a new project I want to talk about. It's quite a in-depth, large project. Probably going to be quite a few videos spread out over quite a long time. So we may go a number of videos between each segment on it because of how in-depth this series is going to be. First, let me show you the first part I got in for it, and then we'll get into the project. We'll talk about what we're going to do, and it's going to be an expensive project, by the way. What I've got here is a Elcro HMI 7-inch display screen. And I have been using Nexeon screens in my projects, like my home-built HF rig and my home-built amplifier that you may have seen a number of times. And I really liked them. I really, really liked them. But I saw this and thought, this is half as much money, same size screen, same resolution. It's got a few potentially pluses to it. One being that it has, instead of just having a dedicated processor run the screen, and you have a separate processor that you tell it what to do. It does everything for the screen, and you basically input back, and you input back to it. This one actually allows you to program the ESP32 that's in it and use it. Now, I don't know if this is going to work out for me. This may be just playing around with a new screen to see what I think, and then going to a Nexeon. But it does have some interesting things. It's got I2C. I bought the acrylic case with it, which was like a couple dollars. So I went and got it just to have it. But you've got GPID, I2C, I2C here, another GPIO D mark. You've got a UART here. You've got a USB-C UART here to hook to the computer. And then you've got a battery input. You've got a SD, micro SD, and you've got a speaker connection. And so I don't know a lot about this. I know the very minimum. I'm going to have to play around with it, learn a little bit, see if it's going to work for us. But what you want to know is, what do I need a screen for? What's the screen for? Well, I have really longed to own, although I don't necessarily need it, but how often do we really need the things that we want? I really wanted to have me something like this. Is a voltage calibrator. This is Ian Johnson's design that he sold to this company. It's about $500. It's kind of pricey for me, but really nice device that lets you pick any voltage from anywhere from 0 to 10 volts in 10 microvolt steps. Has a LM399 reference in it. I think they're using an ADR 1399 now. The new company has switched that, but gives you a pretty stable, pretty darn good device. I understand it works very, very well. As you saw, it's like $500. And what I'm going to do is probably going to end up costing me maybe that much. But my other option was I could go out and get something like this old flute. Now here's an old flute, old analog technology, doesn't work. So you're taking a shot there, and you're going to have $450 in it just broke, and hope to get it working. So my thought is, I can spend that kind of money and build something myself. And let's face it, buying the Ian Johnson's little thing is great, but I won't get near the joy out of it as I would building my own. And what got me on this kick to decide to do this is I couldn't really build anything better. That kind of held me back. But a new part that's come along has got me all wound up, and I think I can build something very, very precise if I take due care. Now, I don't consider myself a volt nut. I don't have the knowledge and everything these volt nut guys do. There's some Marco reps and them guys. They're like eons beyond me when it comes to this kind of electronics. When you get into this nut bolting with these references and stuff, but I think this ADR 1001 will make it easier for me. And the reason is, let's take a look at the data sheet. I'm going to jump on the computer, pull it up, and we'll talk a little about it. and then I'll kind of show you what circuit I'm going to lay out and kind of where my starting point is. And I probably will get $300-400 into this before it's over, but I hope to have a really neat device, and that device is going to be interfaced with this 7-inch touchscreen or a Nexeon 7, one or the other. It'll be completely touchscreen. It'll be much more like a high-end lab device, newer technology. And so that's where I'm going, trying to make something that looks nice, works well, and is very accurate and very stable, something that you can calibrate and have a very, very good reference for at least a year, maybe more. Anyway, let me get over the computer. Let's talk about what we're going to do. Okay, here's what's got me going. Analog, it's not, it says newest product. I guess it's been out for a little bit. Really came on my radar very recently. The analog device is ADR 1001. Now, what this is, it's an LTZ1000. If you're familiar with that as a voltage reference, it's kind of up till now, that's been the holy grail of references. All the volt nuts love their LTZ1000s. Very, very high-end voltage reference. What's happened is they've built a lot of circuits around the LTZ1000. Now, one thing I noticed, it seems like you can't get the LTZ1000 anymore. They've made it special restricted use or something. I don't know. They've done something. It doesn't seem like you can buy them at the moment, but they have this new device out. Now, if you've ever watched any of the Volt Nuts build these references, and you may not have, but if you ever have, one of the things is these do not put out like 10 volts, which is typically what you want, or 5 volts. They put out usually like a 6.6 or 6.95, the different references, high-end references. And what they do is they have to use very precise resistors. They usually end up using Vishay bulk metal full resistors in a metal can with oil in it that gets the drift temperature coefficient down real low to allow them to use it as voltage dividers to get the output they need. They're usually using an op amp and these precision resistors to buffer the output and tune to exactly the output they want. They can get these very good because, as I said, when you're spending $80 on Vishay metal bulk film resistors and using an LTZ 1000, you're going to get a very, very good outcome. If you're using a good op amp, you design the board well, everything is good, you'll get very good output. But one of the things you can't get away from is these references are precision buried Zener diodes, and they're heated. There's a heating element in here that operates at a fixed temperature so that the temperature coefficient, the TempCo, as we call it, isn't much of a factor because we're not going to let the temperature change. So we don't have to worry about TempCo so much. So we can get very precise by holding the temperature very precise. And that's what these chips do, including this chip. And from now on, I'm going to call this the AD Golden Child because look at it. It's gold plated. The one thing they can't get away from is when they design their boards is that their resistors and stuff are outside of that thermally controlled chamber. And so, you've got some different temperature shifts going on and air currents moving across the boards and stuff. So they get into some very interesting things to control that. What's different about this? Well, what they did is they turned around and they built basically an LTZ 1000 in a chip, and they put the resistors you need and such in there. They laser trim them, their own chip, thermally regulated match resistor dividers, so that you get 5 or 10 volts out of this thing precisely. And it's going to be at the same temperature all the time as the rest of the chip internals. So that helps out with temperature drift. So that kind of makes it a little easier. And that means you don't have anything more to buy. Now, these are more expensive than the LTZ 1000, but not that terrible much more. You're looking at probably $30-40 more. And you get the op amps are built in. So the load op amp is built in here. So it stays at the same temperature. And so it doesn't have a TempCo issue where it moves around. By doing so, their hope is, and they believe, you can build much better reference-based devices using this. The whole thing is tuned to, trimmed out to be within, worst case scenario, 0.25% initial accuracy. Of course, we're not so much worried about initial accuracy. We can trim our devices. We're more concerned about how much it's going to drift, and that it's going to do very, very little. It gives you a precision 5 output plus or minus 0.25%. The 5 volt output noise, 1.1 hertz to 10 hertz, is 0.13 ppm peak to peak. That's very good. That's very quiet. This is what you're looking at. This is what's in it. And if you look at this, what you pick up on is you've got your buried zener in here. You've got your matching transistor, which these two have opposite temp codes, so they balance each other out. And then, you've got op amps in here to handle like the buffering, output buffering and such. So it's kind of an all-in-one. In this case, they've got it set up for 10 volts, but the normal is 5 volts. If you hook it up to take advantage of these resistors here, you can get 10 out. You can get it 2 times and end up with 10 out, or you end up with 5 out natively. So this is the device. What you've got to feed it, you've got to feed it for the heater. You've got to feed it to run the chip. You've got some components here to set things such as your RI set, which sets the Zener's current. So anyway, that's this is the heart of this next project. Now, the bad news about this is if we go over and look at the details, this little jewel costs almost $123. So right off the bat, the first part we buy is going to be, get us up there. It's going to be a very in-depth project. I hope you're interested and want to follow along on it. Now, let me show you. I'll pull up Dip Trace and go to the schematic capture, and we'll design out my thoughts. Because not only do you have to have this, you've got a very quiet device here. We're looking at some very low noise figures in this thing. That's outstanding. If you're going to try to play around with 10 microvolts at a time, you're going to have to be down there very, very quiet. You can't have stuff generating 20 microvolts of noise if you're trying to look at 10 microvolts. So we're going to have to build a very quiet power supply for this thing. Everything's going to have to be very, very quiet. And so you're going to see me using some chips here I've never used before that are pretty pricey. The voltage regulators I'm looking at are like $10 a piece, as opposed to my typical, 35-cent 7805. So I've picked some nice stuff out. So let me go lay it out in the schematic capture real quick and let you see what's ahead of us. Okay, let's go ahead and throw together here. First of all, we'll use this because we've got to get a positive and negative rail off that 24-volt battery. I'll do it. And we are positive, and then we're going to need a regulator for the negative. So, yep, that'll do it. That's a good quiet part. We'll set him up, and we've got to set up a set voltage for negative 12. Yep. Let's do the same thing over here. We'll do positive 12 and get our positive rails. That should work. And we need our same resistors. And that gives us our positive. Now, how about a 5 for our digital to analog? He won't run on 12, so we'll just generate 5 volts here for him. Yep, that ought to work. Got to bring the golden child in now. And yeah, the money. Here's the money part. Let's get him all hooked up. We want that stable voltage. We want that 5-volt ref. Yep, that's what we want. We want them low ppm movements. Okay, let's get it hooked up as a reference to our digital to analog and get him powered up. Get that 5 volts. Got to feed him over. We're going to go over to the op amp here. We're going to do a little buffering with a little bit of boosting. Yeah, we're going to need to double that so our 5 volts can swing 5 to 10. That'll work. There's our out. We got to communicate with the digital analog converter, so we better do a little optocoupling over here like this. We want to keep the powers separated. We don't want our digital noisy nasty stuff that's sending the data over to interfere. So we'll just buffer it with an optocoupler and keep all of the 5 volts from the digital separate. And yeah, I think this is going to work. Yeah, I think that'll work right there just fine. Okay, now that I've kind of let you in on what I'm working on, now you can understand why I need a screen like this. I thought maybe we'd plug this in. There's like demo code on it. Just take a quick look at the demo and just see how the screen looks. Hopefully it'll show up on the screen here for you. Let me get some power plugged into it. And there we go. So we got a little demo application here. Touchscreen works nice. They're just demoing some of their different things. It's supposed to be color. If I hit, go like change color maybe. I can't see where I'm because I'm got the camera here. I'm having to back away, so I'm doing this from an angle. So forgive me if I'm missing when I'm touching stuff. There we go. So you can change colors. Light blue. There's some different graphics to kind of show you what the system can do. So it's pretty neat. Nice looking screen. Not bad. Having you calibrated the touchscreen, it's working pretty good. So anyway, this might be the front end to our device. So what I'm going to do is I'm going to do some videos talking about the different components I've chose. You saw me quickly do the little schematic. Of course, that was a little bit of a con. As you probably figured out, I actually was just, I'd already done it. I deleted it and reversed it. It's an old trick. But it gives a quick look and you can see, and it's not so boring sitting there, tracing things out. But anyway, you get the gist of what I'm up to. And so you saw these components I threw out there. Now what I'm going to do is I'm going to walk through it. I'm going to show you the components, and we're going to do some analysis of them and explain why I chose this, why this is why we have to spend the money on this better regulator. Give you some. What I'll do is do some simulations to show you the noise out of like the high end and the same circuit with the cheaper regulator, and show you the kind of noise difference and why you just would not be able to make this an effective device. So my targeted goals for this is 0 to 10 volts with a resolution of 10 microvolts, much like Ian's little device, with the very high end. Instead of an LM399, go with a very high end reference. Going to cost more money. Build it into a small bench top box, not a portable little thing. Instead of having it where when you turn it off, the reference goes cold, which for those that are into volt nutting or watch volt nuts, you'll know that if you turn those things off and warm them back up, they tend to change very little bits every time you do that. So in a real high-end device, what they do is they calibrate it, they get it up to temperature, they calibrate it, and they don't turn the reference off. And so in my device, that's the target. We're going to have batteries in there that will allow it to run all the time. Even if I want to take it, put it in the truck, drive a couple days somewhere to let somebody calibrate their bench with it, there's enough battery in there is the idea that we'll be able to do this. But at the same time, while we're pulling AC in to charge the battery, I don't want to be getting noise into the system. So likely we'll be turning that off when we actually use the device. Going to use a lithium iron phosphate battery because they don't catch fire like lithium iron batteries do. A lot safer to have in your lab. And this is going to be pretty well an open source. I'll show you everything. And that way, if someone wants to replicate it, they're welcome to it. I'd wait until I get it done and make sure that we end up with something worth having. This project could go sideways. It's always, failure's always an option. So anyway, that's where we are. I hope this is something you guys are going to find interesting. And I hope a bunch of you will tune in to watch it because Lord knows I need the viewers. So till next time, I hope to see you in my next video.